Okay, in our last video, we defined what we meant by a basis for a topology. And so what we're going to look at now is an example of showing that a particular collection of subsets of a set defines a basis for a topology. And that's kind of how we're going to show that really is a topology. So the space that we're going to look at is the set of all real numbers, and the topology that we're defining on this that we're going to show is actually a basis for that topology as well, is the set of all open intervals from A to B. And remember that we define elements of a topology to be open sets, right? They're these subsets of our space, and if they're in the topology, they're part of that subcollection that satisfies certain properties. We call them open sets. Well, most people, when they hear the term open set, it's these open intervals that they're thinking about, because most of us are familiar enough with the set of real numbers, and we're maybe not as used to some of these other topologies that we're going to define a little bit later. So we're going to start out with the one that's going to seem familiar, but unfortunately it does require us to use this basis definition in order to show that it's a topology. We'll use the standard formal definition of a topology to show some different topologies on our set of real numbers. Okay, so recall that in order to use our basis definition, so let's go back there, we want to show actually that this set of open intervals generates this topology. So given any one of these open intervals, we're going to need to find a basis element that contains any given element in that interval, but that's completely contained within our given interval. And we also need to make sure that these are indeed basis elements, and so we're going to have to check these criteria as well. So let's see what this is going to look like. Okay, so let's kind of state what we have here. So given an open set AB, that is a subset of the set of real numbers, and some generic element x, so a real number x, in that open set. Okay, what we need to do is we need to find some open set in this basis, so we're going to call it B, such that X is an element of B, and B is contained entirely inside this open interval A to B. Right? So that's what we need to find to satisfy that first criterion. Well, remember we're looking at open intervals, right? So let's just kind of draw this out. I like pictures. So here's our real number line. Here's our open interval A to B, and there's some element x. Okay, well, this distance here is the absolute value of x minus a, and this distance here is the absolute value of x minus b, right? So what we can do is we can take b to be the open interval x minus absolute value of x minus a over 2 and x plus absolute value of x minus b over 2. And so what that's going to do is it's going to give us this new open interval that is contained entirely inside there. Okay, so that, so what we could say, so x is definitely inside b, and b is definitely contained in our open interval a to b. Okay. All right, so that satisfies the first criteria for a basis element. Our second criteria is this intersection thing. So let's assume we already have a basis, and let's let the open interval a to b and the open interval c to d be two basis elements. And we need to take some element, some real number in the intersection of them. So let's maybe call this one y. So let's let y be in the intersection of AB and CD. Okay, so again, we need to find some basis element, so some open set B, such that it's a subset of our intersection and y is an element of B. Okay, so realistically, we would have to look at a number of different cases here to see how these open sets AB and CD interact with each other. But we're just going to look at one case. You can check the other cases on your own. So I'm going to say, without loss of generality, we're going to assume that A is less than C is less than B is less than D. Okay, so our other cases are similar. So to draw a picture here, we have these two open sets, AB and CD, and we have our element Y in the intersection. Well, we can say then that CB is an open set that satisfies these two criteria. CB is definitely a subset of AB intersect CD, and y is definitely an element of CB. So check the other cases on your own.